Hello and welcome to the Unit 10 podcast on Section 16.4. Today we'll talk about how to calculate enthalpy changes. I'm Mr. Sakaguchi,
And I am Mr. Lin.
and let's get going. So one of the things we're going to talk about is Hess's law. And the idea here behind Hess's law is that if we can basically take several thermochemical equations and add them up to get an overall reaction, and the sum of the energy changes for the smaller equations that add up to the larger reaction will basically be the overall enthalpy change for the reaction we're really interested in.
So there's a few things to keep in mind as far as dealing with Hess's law that we're going to go over with you guys. So first up is lining up the equations by the arrows just to keep things nice and neat so you can easily identify where things go. And then on the side, write the delta H down for each of the reactions.
So we're going to add up these equations to get basically the equation we're really interested in. And if you remember some of the net ionic equation stuff we did, things that appear on both sides of the arrow gets eliminated, so we'll be doing something like that.
Also keep in mind that whenever you have to alter an equation by reversing it to fit in with your overall overarching chemical reaction, that if you reverse the equation, then the sign for the enthalpy also gets flipped. So if you flip it around and it was a positive delta H, now the delta H value has to be a negative.
There may be some instances also where you might have to multiply an equation by a factor to get things to eliminate. And if we do that, then the enthalpy also gets multiplied by that same number.
And this is done sometimes so that you can get the number of moles or the balancing to work out in the end. And when you do that, right, you multiply it by the enthalpy.
Yeah, because remember the goal of this is through adding multiple equations together, it has to look exactly like the final equation that we're interested in.
Right.
So here's an example of Hess's law. Let's say this reaction is the one we're interested in and we want to know the enthalpy change. And they give us these two reactions in order to basically use these and manipulate them to get this reaction here.
So what you're going to be paying attention to are where the given reactions line up with our wanted overall reaction. So for instance, we've got 2 carbon monoxide in that first reaction, and that lines up just fine with the desired reaction. So we can keep that as is, copy that down. And then the second reaction, however, it looks a little different. For instance, you notice that our desired reaction has nitrogen gas on the product side, but in the given reaction, it's a reactant. So what we're going to do is we're going to flip this around. So when you flip the equation, it's going to look like this down below. So now that our nitrogen gas is on the product side, which is what we wanted, and since we flipped it, our delta H, our enthalpy for that reaction, for reaction B, is that the enthalpy will change and become negative. Now, when you add up the two reactions in this manner, you'll see that certain things cancel out. For starters, the oxygens in the first reaction is going to cancel out with the oxygen in the second reaction because now they are on opposite sides of the arrow, and if it's kind of like an algebraic expression, if you have the same thing on both sides of the equal sign, they cancel out, and this is the same here for the chemical reactions. When you put it all together, you have your carbon monoxide, you have your NO, everything else lines up just to look just like our above desired reaction, and then we add up our delta H's, which we have manipulated accordingly, and when you put it together, you get your proper delta H of negative 746.6 kilojoules.
That's right. Another way to measure changes besides using Hess's law is standard enthalpies of formation. These are basically the energy changes that accompany the formation of compounds from the elemental components.
So when these were found experimentally, and there's a large chart of these, and what they're saying is whenever you're forming these compounds in the first place, putting together these compounds causes an enthalpy change, and they recorded all of these, and what you do is add them all together. So below here, well, rather, to calculate this, there are 2 simple steps. First, you find the standard enthalpies for each substance, and that's on the table. You look it up. Individual elements can be ignored. So we're talking about diatomics like hydrogen gas and that sort of thing. And then you're going to look at your products, the delta H of formation of the products. You're going to add up all of the enthalpies for those products, and then you're going to subtract them, or you're going to subtract out the enthalpies for your reactants. And when you put it together, that's your enthalpy of the reaction.
One thing to keep in mind is the reason why elements have standard enthalpies of formation of 0 is because we're starting as the element state. The idea is that any energy other than the elemental state is actually energy that you could use for other things. The energy inherent to the element is what we standardize as 0. So here's an example of a standard enthalpy of formation problem. So what we would have to do is we'd have to look up our enthalpies of formation for each of our elements. Okay, so it's products minus reactants. With our balance coefficients that you see in our equation, we're going to have to multiply our looked up values by these numbers. Okay, so the products are on this side. So NO2, so we need the standard heat of formation of NO2, and we're going to multiply it times 4. And then we'll do the same thing for water times 6, and then we'll subtract out the NH3 and the N7O2s. Now, one thing to keep in mind here, guys, is that the state of matter makes a difference. So you have to keep in mind what the state of matter is when you look up these values. And notice how oxygen is 0, just like as we said, because it's an element. And then these are the numbers for our NO2 and water, and this is our NH3. And so when we multiply, add up, and then subtract, we end up with this many kilojoules. And so now we know that this is an endothermic reaction. That's it.